Next, we come on to the idea of surface energy. So, that is something which we discussed in brief while discussing surface tension. So, the idea or the formula we have already discussed, but its context is missing here. In case of a simple liquid, although there is nothing simple like a liquid, if you have, let's say, liquid is there, so that liquid will have some surface. We say that surface energy is that extra energy which the particles on the surface have in comparison to the particles in the bulk. So this is applicable in cases of spherical liquids as well. By spherical liquids, I mean drops and bubbles. So if you have some kind of a drop, that means like a water drop. So it has a surface. Even a water drop will have that extra surface energy by the virtue of its uh, surface. That is the spherical shape which we actually see. In fact, the system that of water drop wants to minimize its surface energy, and for a given volume, the minimum surface area is that of a sphere. That's why water drops are spherical in nature. But if we are talking about surface energy, then what is its expression? So, for a water drop, we have one surface. For a bubble, we have two surfaces. So, this is a drop and this is a bubble. So, surface energy of a drop is the surface tension of the drop into the surface area of the drop. So what is the surface area of a sphere? It is 4 pi r square. So this is the surface energy. Uh, so formula itself is not as important. Important thing is that uh, what are we multiplying with what? So we are multiplying surface tension with the surface area of the sphere. Next, in case of a bubble, for a bubble, how many surfaces are there? So that is a tricky part. There are two surfaces. First surface which is inside and second surface which is outside. So the radius of the bubble is, let's say, some r. So we'll say it would be some 4 pi r square, the surface area of the inner surface, and that of the outer surface will also take the same. So it is simply multiplied by 2. So that means that there are not a lot of difference in the formulas for a drop and a bubble, except this two factor. It's like a twice, two times doing thing, uh, but otherwise they are pretty similar. So this is the question which we have: what is the surface energy of the soap bubble of radius r and surface tension s? So we have answered that question. The surface energy of a bubble of radius r and surface tension we have taken sigma is this value. Now, now we basically have questions where the bubble size is increasing. So when we increase the size of the bubble, what do you think will happen? The surface energy of the bubble will increase, not only because we are increasing the size of the bubble, but we are bringing more particles on the surface of the bubble. That is what we mean by increasing the surface energy of uh, a system, like a bubble or a soap, or a soap bubble or a drop. We are bringing particles from the bulk of the liquid, that is the liquid drop, and we are placing those particles on the surface. So when we do that, we require energy. So the question asks in that way, कि what is the work done in increasing the size of the bubble? Work done means that we'll have to supply some work or supply uh, some form of energy in increasing that surface energy. So that work done which we are doing, it goes into surface energy. So what is the work done in increasing the size of the bubble from a radius of 3 centimeter to 5 centimeter? So we are given some options. Let's see. So we have to answer in terms of pi. Okay. So let's begin. We have to increase the size of the soap bubble. Yes, it is a soap bubble from 3 centimeter to 5 centimeter. So we are blowing inside the bubble. Okay. So when we were kids, we really liked that idea of blowing the bubbles. And they used to, fly around. So, uh, work done is equal to surface energy, or the change in the surface energy is equal to surface tension 0.03 into the change in the surface area. So that would be 8 pi r f square minus r I square. So I have already taken factor 2 inside. So this 4 pi has become 8 pi, and that's that. So this becomes 0.24 pi 5. I'll put the value 5 here and put the value 3 here. So this is 5 square minus 3 square. So this will be 5 plus 3 into 5 minus 3. So it would be some 16. So it would be 16 uh, centimeter square. So 16 into 10 to the power minus 4. Something like that. Joules. So 16 times 24. This is 64 into 32. So this is um, 3.84 pi into 10 to the power minus 4 joules, or this is some 0.384 pi millijoules. So options A is 0.2, option B is 2 pi, option C is 0.4 pi, option D is 4 pi. So our answer matches is closest to option C. So that is 0.4 pi. Next, we have a question of two mercury drops. Uh, each of radius r, they merge to form a bigger drop, the surface energy of the bigger drop would be. So this is rather trivial question. We will simply say uh, that what is the surface area of the final drop. So that we can find by uh, adding the volume of the two smaller drops. And after adding the volume, we'll calculate what is the radius of the new drop and what will be the surface area of the new drop. From that, we can find what is the surface energy by multiplying the surface tension with 4 pi r square. Okay. So again, this question also has probably come in JEE mains as well. A large number of liquid drops, each of radius small r, coalesce to form a single drop of radius r. The energy released is converted into kinetic energy of the big drop. Find the speed of the bigger drop. So this is like a fun question. If we have a lot of drops of radius small r, let's say we have some capital N number of drops, and all these drops combine to form a bigger drop. What will happen is that there would be a release of surface energy. So this happens. Uh, you would have seen this example when, let's say, if you are uh, uh, drinking a glass of cold water, then perspiration forms on the outside surface of the glass. The outside surface of the glass, these small drops, they start going down because of gravity. But while going down, they coalesce, they combine to form a bigger drop. So why does that happen? Why do they combine? What is their need? Just because they're close to each other, is because they want to decrease the surface area of their own drop. By decreasing the surface area, they decrease the surface energy. So this releases the energy for the system to overcome the further whatever path they are going through. So that's actually how systems behave. Even if a small drop is there, it would want to decrease its energy by combining with other drops or by decreasing its surface area to a sphere. So the radius of the bigger drop is given as r. So if I were to find what is the number of drops, let's say, so I can write an equation that 4 by 3 pi small r cube times capital N is equal to 4 by 3 pi r cube. So this implies that r into n to the power 1 by 3 is equal to capital R. If we take a square root, cube root of. So this is the equation which we have. So here we are not looking for like a very optimal way to solve the equation. But when we have uh, basically some idea that in which direction is question going to go, then it also provides us with lot of calm while solving the question. So that's why I'm taken the number of drops as capital N, and I'm very sure that this number of drops I'll be using in the final result. Uh, then we say that okay, um, what would be the kinetic energy of the final drop? So that would be evaluated by finding the change in surface energy. So the initial surface energy should have been higher, right? So if initial surface energy is higher, final is lower, then that difference will go into the kinetic energy of the system. So I will say half density 4 by 3 pi r cube into the speed of the drop squared is equal to 4 pi r square n times n drops into surface tension S minus 4 pi capital R square into surface tension S. So we basically don't want capital N in our expression. So capital N will have to substitute. So uh, like I said, I knew that I'll be using this capital N. I can put that value. So when I put that value, I'll get R upon small r cube into 4 pi gets cancelled out into r square into s minus r square into s is equal to half rho r cube by 3 into v square. So basically this would be r cube upon r into s minus r square into s is equal to rho by 6. So we'll divide this by r cube. So this would be s 1 upon r minus 1 by capital R is equal to rho by 6 into v square. So this comes out to a pretty good result actually in terms of how it looks. So this was also a question of JEE mains only. Um, Other questions also come on this idea, and that is of drops and bubbles. So they basically nowadays trend is to combine thermodynamics with this topic. So be on the lookout for that. Thank you.